In this video, we're going to talk about the infinitesimal change in some variable that depends on at least two other variables. So for example, we have a variable f here, which is some function of x and y. And what we'd like to do is we'd like to figure out how does f change as x and y change. So here we can imagine that x and y lie on some 2D plot, and we want to change our values of x and y infinitesimally. So we allow x to change by some amount dx, and we allow y to change by some amount dy. And as we do this, we want to figure out how much does f change. So we'd like to find df. So first, let's think about what if we only change x. So we're not going to follow the straight line path where x and y change at the same time. We're going to change one and then the other. So if we change dx, or x by some amount dx, then we can say that the amount that f changes, df along just this path, would be partial f partial x times dx. And the reason that this is true is the partial f partial x tells us how much does our function f change if we change only x. So we're holding y constant in this partial derivative. We're moving only in the x direction. This is our rate of change of f as we change only x. And then we multiply it by how much did we change x? Well, we changed it by dx. So that tells us how much df changed along just this blue path here. Now we can make the same argument for dy. If we now move along some path dy here, we can write df as partial f partial y. How much does f change when we change only y, multiplied by how much did y change? And that gives us df along this purple path. Now, if we want to move from this dot here to this dot here, we want to move both in x and in y, we can simply add up the change along this path and along this path, and we end up with partial f partial x dx plus partial f partial y dy. That is the total change in f, our function that depends on x and y, as we move from along the x direction only and then along the y direction only. As just an additional note, often we write df where we put a subscript on the partial differentials here, the partial derivatives, to tell what we are holding constant. So this is really the exact same thing as this, because when we take a partial derivative, we assume that we hold these other variables constant, but it's often written explicitly in terms of what we are in fact holding constant. So this is partial f partial x with y held constant, and this is partial f partial y with x held constant. Now, in the case that you have more than two other variables, or that x and y can be written in terms of some third variable, say z, it may actually be useful to say what we are explicitly holding constant. As a simple example of this, we can define some actual function f of x and y. We can take the partial derivatives of f with respect to x and y, and then we can write down df as the partial derivative of f with respect to x dx plus the partial derivative of f with respect to y dy. And this can be done for any function. This is just an arbitrary function that I chose